So my 2.5 second break is over. And seconds, by the way, are recognized as not only imperial, but metric. So I'm going to talk to you briefly about the metric system. And I'm going to pretend that we have a cube. And this cube is a cube of water. And no, I don't draw very good cubes, but that's okay, especially on a touchpad. Oh, I should have gotten my Wacom tablet out. Let's see if I can do any better on this. But if that cube happens to be, and I do it, 1 centimeter tall, 1 centimeter deep, and 1 centimeter wide. Hey, my new tablet's working. I just got it yesterday. First thing I wrote with the new tablet. Are you impressed? So here's a cube, 1 centimeter by 1 centimeter by 1 centimeter. That lived in my pocket for a month by the looks of it. But it's water, so what can we say about that? I have 1 centimeter. Centi means 1/100th of a meter. So I've already defined something called distance, right? Or length. I have 1 cubic centimeter, right? Which is volume. And 1 cubic centimeter actually happens to be exactly 1 milliliter. They're the same. 1 centimeter cubed is a milliliter. Milli is 1/1000th. So I've got volume either in cubic distances or in the typical volume measures of liters. And what if I were to take a measure of that, put it on a balance or scale and measure that? That would be the same as 1 gram. Whoa, what happened there? I got to get used to this pen. 1 gram. So now I have a measure of mass, which isn't the same as weight. We'll get into that later. What if I were to put some heat under that and I were to, wow, this is strange. That's supposed to be a triangle. The triangle in chemistry represents heat. And if I were to put in 1 calorie of energy, I would raise the temperature by 1 centigrade. So I have energy in the form of calories, and I have temperature in the form of centigrade or Celsius. And I haven't left this cube yet. Now, the actual formal definitions of these metric units, centimeters, milliliters, grams, calories, centigrade, they're much more complicated science to be extremely precise and defined in a way that are extremely precise. So what I'm telling you here is just true, but accurate. Yes, it's hard to be as precise unless you define it in much more complicated ways. But I'm not talking about body parts of kings or fancy shoes of kings. I'm not talking about anything like that. This is all based on simple, repetitive, scientific observations. Okay? Now, I mentioned mass and weight. Let me just show you something here. Mass is something that is measured with a balance. And so if I have Holy moly. I'm not sure what the heck happened there. Let me try this again. Why is that all going away and this is not? That is so strange. Bear with me, folks. So I have mass measured with something called a balance, not a scale. I make this mistake all the time. And I have some unknown here. I'm going to put weights on this side, weights of known mass, and just keep stacking them up until the device balances, because gravity is pulling the same on both sides. And it doesn't matter if I'm on the moon or if I'm on Earth or I'm on Pluto. As long as I have gravity, I can measure something and the mass doesn't change. The mass is the same everywhere in the universe. Don't pull out some technicality in a black hole or whatever. But for all practical purposes, the mass is unchanged. And we measure the mass in grams, kilograms, or metric tons. Weight, on the other hand, is measured with a scale, and more accurately, we call it a spring scale. And so you have a spring attached to something, and a pointer, and some sort of measuring device. And you put whatever you're going to measure there, and it depends on how far it pulls the spring. Now, this does depend on where you are in the universe. So my weight changes if I'm here on Earth, or I'm on the moon, or I'm on Pluto. Weight changes. So weight and mass are not the same thing, but we can convert between mass and weight between the imperial weight system, pounds and ounces, to the mass system if we make one assumption. Gravity is consistent. And gravity is specifically what we have here near the surface of the Earth. Now, in scientific accuracy, we would even need to know our elevation, because weight will change even from here to Colorado or here to any other place at a different elevation. Weight will change. And does it change enough for weighing pallets of lettuce? No. Does it change enough for scientifically, technically accurate measurements that you might need to take for some scientific research? Absolutely. The simplest way to lose weight, go up in an airplane. You're going to lose more weight than you might think, but not enough to matter, right? And it's going to be right back. You didn't lose anything. It's going to be right back as soon as you land. But there is a small weight loss when you go up in a plane. Your mass did not go anywhere, so it's still there. And so that's why weight and mass are different, and why you cannot have conversions between weight and mass unless you make the assumption that we're talking here on Earth, relatively close to sea level. And in agriculture, that's a pretty darn good assumption, right? That's a really good assumption. And so you just have to keep in mind that if you're talking about doing agricultural research that's going to be done on a space station or being done on Mars, weight and mass are not the same thing. And nobody's going to talk about weight. Weight is useless. It's all about mass and metric. So let's take another very brief break, and I'll be right back to keep on going with this lecture.